Think you understand dark matter? For decades, physicists have been chasing invisible particles that make up 85% of all the matter in the universe. Particles we can't see, can't touch, yet somehow hold the entire universe together. What if this whole hunt is built on one assumption we've never actually questioned? Let me show you what Richard Feynman would make of it. January 2026. A new quantum field theory paper drops something radical. What if gravity isn't equally strong everywhere? What if, instead of inventing invisible particles, the real answer is that gravity itself might behave differently? To understand why this matters, we need to go back to the exact moment scientists hit a mystery and chose a path we're still stuck on today. 1933. Fritz Zwicky pointed his telescope at the Coma galaxy cluster. He measured the speeds of the galaxies moving within that cluster. And something was completely wrong. The galaxies were moving too fast. Picture a merry-go-round spinning. The kids on the edges have to hold on tight, otherwise the centrifugal force would fling them off. The speed the carousel spins depends on how much force they can exert to stay in place. Now apply that to a galaxy. The stars on the outer edges orbit the center. The gravity from the center is what keeps them there, like the kids' hands holding the bars of the carousel. But when Zwicky measured the speeds, the stars were spinning way too fast. The gravity from visible matter alone shouldn't have been strong enough to keep them in place. They should have been ejected into intergalactic space. Yet they weren't. They stayed perfectly in orbit. Stop. Think about what that means. Two possibilities. 1. There's extra matter we can't see providing the additional gravity to hold them in place. 2. Gravity behaves differently than we thought at galactic scales. Zwicky chose option 1. He proposed there must be missing matter that doesn't emit light but does exert gravitational pull. He called it dark matter. But why that choice? Why did scientists, over the next few decades, go all in on dark matter instead of questioning gravity itself? The answer: math. Einstein's general relativity perfectly explains black holes, gravitational lensing, and cosmic expansion. It has an incredibly elegant framework. Modifying gravity means rewriting that whole framework. It means admitting Einstein was incomplete in certain situations. But adding invisible matter, that slips right into general relativity. The math stays the same. You just add more mass to the universe. Mass we can't see but that the math says has to be there. And so, cold dark matter, or CDM, became the leading theory. Invisible particles, probably WIMPs, weakly interacting massive particles, maybe axions, or something else entirely. Particles that don't interact with light but have mass, so they produce gravity. Think of it as invisible cosmic glue holding galaxies together. Beautiful explanation. Mathematically sound. And it rests on one big assumption: that gravity, exactly as Einstein described it, works on all scales. The problem is missing matter, not the theory itself. But consider the Emperor's New Clothes story. Everyone agrees he's got on amazing clothes because they've been told to believe it. No one questions the premise until a kid yells, "He's naked." What if dark matter is our version of that? What if we've spent decades building detectors, running simulations, and churning out thousands of papers about invisible particles? All because we never questioned the original assumption that gravity works exactly like Einstein said on every single scale? This is where Feynman enters. He had one core principle. Don't trust mathematical elegance. Don't trust textbooks. Don't trust authority. Trust only what you can measure. Trust experiments. Trust observations, he said. It doesn't matter how pretty your theory is or how brilliant you are. If it doesn't match the data, it's wrong. Would Feynman doubt dark matter? Definitely. Not because it's impossible, but because it's a theory built on absence. It says, there's something invisible, undetectable, but the math says it must be there. Feynman would challenge it. He'd demand, show me the particle. Show me actual proof. Until then, stay skeptical. Keep alternatives on the table, including the possibility that gravity itself, the gravity we might need to rethink. So, is there a real alternative? That's exactly what the January 2026 research tackles. Quantum field theory meets gravity. The pitch. What if gravity's strength isn't fixed everywhere? What if, under specific conditions at specific scales, Gravity acts differently than general relativity says? Not because Einstein was wrong, but because general relativity is a classical theory. It doesn't fully account for quantum mechanics. At galactic scales, quantum effects we normally ignore become important, slightly changing gravity's strength. Modifying gravity isn't new. Back in 1983, physicist Mordechai Milgram proposed Mond-modified Newtonian dynamics. The idea was straightforward. At low accelerations, like at galaxy edges, Newton's gravity law shifts slightly. Instead of force dropping off with distance squared, it drops differently. Adjust gravity's math and boom, no need for dark matter. Galaxies spin fast because gravity's actually stronger at the edges than Newton predicted. Mond nailed individual galaxy rotation curves. But there's a catch. It didn't work universally. Couldn't explain galaxy clusters. Couldn't explain gravitational lensing in some setups. And it had no deep theoretical base. Just a patch job, a math tweak with no fundamental theory behind it. Tweaking gravity is like changing chess rules mid-game. You can do it, but you need solid justification. You need a theoretical framework explaining why and when the rules change. Mond didn't have that. It was an empirical rule that worked in some cases, but not in others. And Feynman would be skeptical here too. Proposing a tweak isn't enough. You need a full theory. You need a framework with testable predictions. You need to say, if I'm right, when you run this experiment, you'll get that result. Then you run it and verify. The January 2026 research attempts exactly this. It proposes a quantum field theory framework where gravity's strength varies based on the local quantum environment. Bold move. An attempt to give Mond the theoretical foundation it lacked. But it's still fringe. Most physicists stick with cold dark matter because the evidence currently backs it. Hold on. The evidence points to dark matter? Didn't we just say it's an illusion? Here's the twist. Here's the paradox. Throughout 2025 and 2026, a string of discoveries actually strengthened the dark matter hypothesis, not weakened it. Let me take you through the evidence. Start with the headline, January 2026, China. Researchers claim they spotted the first direct evidence of dark matter. They observed the Migdal effect. The Migdal effect was predicted in 1939. Here's how it works. When a dark matter particle collides with an atomic nucleus, the nucleus recoils. That recoil can cause the electrons around the atom to become excited or even ejected. Think of hitting a table and making the dishes rattle. The collision with the nucleus is the main impact, but the electron vibration is the Migdal effect. Catching the Migdal effect matters because it gives a signature way easier to detect than a direct nuclear hit. It's like an atomic fingerprint left behind by dark matter. The Chinese team says they've spotted that fingerprint. If it holds up, that's direct proof of dark matter particles hitting atoms. This is what Feynman wanted. Show me the particle. Well, this could be it. But wait, there's more evidence. Late 2025, Tokyo. Researchers spotted a gamma-ray halo around our galaxy's center. Gamma rays are high-energy photons. Where's the source? One option: dark matter annihilation. When dark matter particles collide, they can annihilate and release gamma rays. Like matter and antimatter colliding and converting to pure energy. Finding a gamma-ray halo with the right fingerprint's correct spatial pattern and energy spectrum could mean dark matter is actually annihilating. It's like detecting the exhaust of an invisible car. You can't see the car, but you can measure the exhaust gases and infer the car is there. The Tokyo detection is suggestive. It's not definitive, but it's consistent with the dark matter particle hypothesis. Let's zoom out. November 2025. DCAM Collaboration released a massive dark matter map. They used gravitational lensing to trace dark matter distribution across the universe. Gravitational lensing happens when light from distant galaxies bends as it passes through gravity of intervening matter. Measure how much the light bends, and you can figure out where the mass is, even invisible mass. The DECAM map reveals dark matter structures at cosmic scales, and they match cold dark matter predictions exactly, not modified gravity theories. Cold dark matter models predict a cosmic web dark matter, filaments linking galaxies together. And that's precisely what DCAM shows. It's like X-raying the universe and seeing the invisible skeleton holding it together. And that skeleton matches exactly what cold dark matter models predicted. Now jump to October 2025. Researchers studied the motion of 12 faint dwarf galaxies. Dwarf galaxies are small systems with few stars. They're perfect test beds for gravity theories since their motion is simpler than big spiral galaxies. If Mond were right, it should work for dwarf galaxies. It doesn't. The October 2025 data show dwarf galaxies acting in ways Mond can't account for. Their rotation curve star velocities don't match Mond's forecast. They match cold dark matter's forecast. It's like testing a chess rule on a simple board. Doesn't work in the simple case? It's probably wrong. Mond fails in the simple case of dwarf galaxies. Cold dark matter passes the test. And finally, December 2025. The LZ detector, the world's most sensitive dark matter detector at SLAC, dropped its data. No WIMP detections in the 3 to 9 giga-electron-volt mass range. That eliminates one class of dark matter candidates. Hold up. Isn't that evidence against dark matter? Sort of. It rules out certain particle candidates, but doesn't eliminate all possibilities. Lots of other particles could still be dark matter, like searching for lost keys. You checked under the couch, nothing. That doesn't mean the keys don't exist. They're just not under the couch. Search somewhere else. The LZ detector keeps searching. No WIMPs in that mass range, but it narrows the field. It tells us where not to look and points where to go next. Also, November 2025, researchers tested for a hypothetical fifth force. If modified gravity were real, it might appear as an extra force beyond the four known: gravitational, electromagnetic, strong nuclear, weak nuclear. Tests showed any fifth force must be less than 7% as strong as gravity. That hammers modified gravity models hard. If gravity is being tweaked by an extra force, that force has to be super weak. Much weaker than some theories predicted. Quick recap. January 2026. Possible dark matter particle detection via Migdal effect. Late 2025. Gamma-ray halo matching dark matter annihilation. November 2025. Large-scale structure map matching cold dark matter models. October 2025. Dwarf galaxies matching cold dark matter, not Mond. December 2025. WIMPs ruled out in one mass range, but other particles survive. November 2025. Fifth force experiments kill modified gravity models. What's it all mean? Picture a courtroom. Dark matter's on trial. The prosecution, modified gravity advocates, argues dark matter is fake, a math trick we made up because we don't want to rewrite gravity. The defense, dark matter advocates, calls witness after witness. The Migdal effect, the gamma-ray halo, the DCAM map, the dwarf galaxies, fifth force limits. Each witness corroborates the story. No single one is bulletproof, but together they build a case. They point to dark matter particles being real. Then the prosecution calls its witness. The January 2026 quantum field theory research. Bold, new theory saying gravity might shift. Powerful witness, but one voice against many. The jury. The scientific community weighs the case. Right now, the majority backs dark matter. Not because dark matter's proven beyond shadow of a doubt, but because the weight of evidence leans that direction. So what about the claim that dark matter's an illusion? Here's the tough reality. Based on 2025 and 2026 evidence, calling dark matter an illusion is premature. The evidence increasingly supports real particles, not tweaked gravity. But here's Feynman's real lesson. It's not about dark matter. It's about how science actually works. Feynman would tell us to question assumptions, even when evidence backs the mainstream view. He'd push us to stay open to alternatives, especially ones that are testable. He'd say science isn't about finding the right answer and calling it done. It's about never stopping the questions, never stopping the tests, never stopping the refinement. The January 2026 paper doesn't kill dark matter, but it matters because it stops us from getting comfortable. It makes us ask if we accept dark matter just because the math works. And if dark matter ends up being right, if we nail down dark matter particles in the next few years, Feynman's lesson still stands. We'll have found dark matter not by blindly believing the theory, but by questioning, testing, letting evidence lead us. By building detectors like LZ, by hunting the Migdal effect, by tracking gamma-ray halos, by being willing to be wrong. What if the January 2026 modified gravity theory turns out right? If future tests prove gravity really does shift in ways general relativity doesn't account for? We'll have rewritten the physics playbook. Gone beyond Einstein. That too proves Feynman was right. Because we dared to challenge even our sacred theories when the data said so. Bottom line, science isn't about being right. It's about being ready to be wrong. It's about throwing ideas out there and ditching them if they flop, knowing we're never done learning. Dark matter could be real. Could be particles we just haven't nailed down yet. Or maybe we're missing something crucial about gravity. For now, the data points to particles. You came asking if dark matter is an illusion. Now you know. Probably not, from what we've seen. But the real takeaway isn't that. It's that science runs on questions. On trying other paths. On testing without end. That's never an illusion. It's the heartbeat of science. Keep asking those questions, and you keep moving forward. Discovering. Unlocking the universe's mysteries, one test at a time.